What's up guys? So today we've got a really cool project that I'm excited to work on. We've got some PCBs from PCB Way and we've got some parts. And we're going to be building a 400 megahertz logic analyzer, which we'll be able to use to more effectively diagnose consoles like the PS5, which regularly have issues with the South Bridge or the BIOS chips. And we're going to be able to use the tool that we build today to visualize the data communication between things like the PS5, South Bridge, and the NOR. So thank you to PCB Way for sponsoring this video. We've got some PCBs from them in this box, and then we've got a bunch of parts that we're going to use to put this thing together. So real quick, in this box here, we've got a bunch of parts we're going to be using. We've got some mini heat sinks. We have a Raspberry Pi Pico 2, a bunch of pin headers, resistors, caps, switches, all sorts of fun stuff. So I'll put these parts aside for now, but we're going to be coming back to these. And let's get into this package from PCB Way. So I honestly haven't been doing a lot of like data signal diagnostics on these consoles yet. And I'm realizing I'm really missing out on a lot of information without tools like this to be able to effectively fix these consoles. And let's get this thing open. Hey, got a little bag here. Let's see what's in this. Cool. This is like a little ruler. It's got some different footprints on it for various chip sizes. What else have we got? We got another ruler with some more footprints. Got a nice little PCB Way stand thing. That's fun. And then we've got a pen. And I actually really like this bag. I'll probably use this to organize some things on my workbench. God knows I need more organization. Cool, so here we've got the boards themselves. So this is a project by Dr. Gusman. You can see his name right here, along with the GitHub URL on the back of the PCB. So massive shout out to Dr. Gusman for making this logic analyzer. This is a really cool logic analyzer based off of the Raspberry Pi Pico chips. So I've got two Pico chips here that we're going to use and try out. We've got the Pico 2 and we've got the Pico W for wireless. So you can actually use this thing wirelessly with your computer. And he also has this PCB Way link here. I'll put both of these links in the description where you can directly order the PCB without having to deal with KiCad. Or if you want, you can also click this PCB and assembly option. And I actually did grab one here that I got pre-assembled. I think this one came assembled without the Pico chip, so you can just buy the Pico chip separately. This was only about like 35 bucks. So really cheap for a logic analyzer. But here is the pre-assembled one. They even pre-tinned the pads for us for the Pico, which is a nice touch. And we've got Dr. Gusman's logo on the back there. And if you do end up grabbing one of these or building one yourself, definitely make sure to head over to his GitHub here and support him on Ko-fi, because you're going to be saving tons of money on a logic analyzer like this. This thing with the burst mode with the Pico 2 can go up to like 400 megahertz, which is pretty ridiculous for such a budget option for a logic analyzer. So this thing is going to be really powerful for repair purposes, and I'm really excited to give it a shot. I think I'm going to be setting this one up with the Raspberry Pi W, but I don't want to get into all the wireless stuff just yet. But what I want to do first, real quick, is just take a look at the soldering on this, because we can judge PCB Way's soldering abilities here. So here is the board, and this thing is honestly looking beautiful. Yeah, all of these Texas Instrument translator chips here are looking really nice. So this is like some high quality soldering that you're gonna get from a board like this if you get one pre-assembled. And again, it's super nice. They pre-tin these pads here for the Pico chip. And we can take a look at the other non-assembled ones here. We've got 4 other PCBs, nice and thick. And these things look absolutely gorgeous in white. I really like the white and black PCBs. So without further ado, let's dive into building this thing. So one of the nice parts about this is there's not really too many parts we got to put on here. We really just have to put on these 6 voltage translators here with the 2 caps each. We're going to start right over here with the diode and the resistors here. All right, so we've got one of these diodes here, and the black stripe on these types of surface mounted diodes indicates the cathode. So this is going to go on just like this. Before we put this on, I'm going to tin one of these sides. So I'm going to tin the top side. And the reason I'm doing this is just because it's going to make it easier to allow this thing to sit flat. So we're going to put some flux on here. I'll set my iron to 400. We'll turn our fuming extractor on. And let's just get this pad here nice and tinned. That is plenty right there. We're just going to melt this one side on here and let that cool. And you can see this thing is flat against the PCB already and lined up well. We just throw some extra flux on this side and we can get this side nice and tinned up. Let me just get this thing cleaned up a little bit. And that diode is looking great. So I'm happy with that. So let's zoom in and we can move on to these resistors. With a new PCB like this, it can help to kind of scrape the pads a little bit. You can see solder won't stick right away until you scrape a little bit, and there you go. So we've got one side of each of those done, and now we got to grab our tiny resistors here. So we're going to grab these, which are the 8.2 kilo ohm ones. So So I'll show you all of the parts here. Here are the diodes that I got. I'll have links for all of the parts I used here in the description since there's really not too many. And here are the 8.2 kilo ohm resistors we're using now. So I'm just going to pull up here on the film and we'll try to dump out one of those. Perfect. And I'm turning my bent tweezers in this direction so they can kind of sit flat against the PCB. This can be helpful when you're grabbing like tiny components like this. So we're just gonna do that. This is totally fine and you'll see why in a second here. We can just add a little more solder to this side here. Just get some on the actual pad there. And I'm just gonna come in with the hot air. This is leaded, so I'm just gonna go up to like 380, like 60% airspeed. And we're just gonna come in and this thing should straighten itself out just like that. So surface tension is your friend when working with small components like this. These are 0402 components, so they're not like too small. They're pretty manageable. But especially when you're working with 0201 components, which are definitely smaller than this method really helps. So I'm gonna throw those resistors back and we're gonna grab the 100 kilo ohm resistors. That's those right there. And this is the exact same deal. Just gonna try to grab one of these here. I just launched that one somewhere, so this is why we have like 100 of them. Let me just dump that out. There we go. Can flip this thing over and we're gonna do the exact same thing. This might be the first time I'm soldering on a board that's white. So we're just gonna hit that side and then we can get some solder on this side as well. You can really see how dirty the flux gets on the white board compared to like the darker colored boards like green or black. If we wanted to be super extra about it, we could at this point come in with our tweezers and just sort of straighten these out just like that, just applying pressure while melting and the orientation we want them to go, so kind of like this, and then remove heat and we've got a nice straightened out component. Great. So I'm really happy with how these guys are looking up here. We can just give them a nice quick clean. It's from IPA. I really like how this white solder mask looks. It looks super clean. Unlike the diode here, these surface mounted resistors and surface mounted ceramic capacitors here don't have to go on the board any specific orientation. You can just throw them on. With other capacitor types like electrolytics, you do have to worry about the direction that you're putting them on the board. But not in this case. These are ceramic capacitors that we're going to be putting on the board here, and they can go on in either direction. So what you can do with these is you could buy a stencil and you can spread solder paste through the stencil on all these pads and then just sort of hand place all the components, throw it on a heating pad and let it sort of melt all at once. But honestly, for a board like this, where there's only about like 20 surface mounted components, I think it's a little bit overkill unless you're making like a bunch of them. Then obviously, you know, it would make sense to grab a stencil. But personally, I really like hand soldering components like this, especially on boards like this where there's not many components you got to put on. So here are the capacitors. If you're new to surface mounted stuff, these black components here are resistors, and the ceramic capacitors are oftentimes beige colored like this. I see a lot of beginners getting confused between caps and resistors, but that's generally a really good way to tell what you're looking at. So I think my plan here is to solder the two capacitors, then the voltage translator here, two caps, chip, and then just sort of go top to bottom so that I'm not sort of getting in my own way with these capacitors when we go to put on the chips. For these caps, I'll show you a bit of a different approach versus the resistors. Obviously, we can do these in the exact same way we did the resistors. But the other way we can do this is we can just go ahead and tin both of these here. You can see I accidentally tinned these pads here. That's not a problem. We're going to get to that in a moment anyways. But with these two tinned like that, we can just grab the component. Again, I'm holding my tweezers with the flat side sort of down. I really like these tweezers, by the way. These are the best precision tweezers. I'm really a big fan of these things. So I'll put a link for these in the description. They're really a nice in-between with these other titanium tweezers I have that are extra sharp. These are almost as sharp, but not quite as fragile, I find. So they're a really nice in-between, honestly. But yeah, again, I'm going to put the flat side sort of down on these bent tweezers here towards the PCB so that we can grab the capacitor. And grab the capacitor while it's already on the PCB so that it's flat, so that you're not like grabbing underneath the capacitor like this. The other way you can make sure you're grabbing these flat is just to push down with another pair of tweezers on top like this and then grab it again, and then you can be sure that this thing is flat against the PCB. And now we can grab some hot air and come in and just hold it over where it needs to go. Don't push down too much. Allow the solder to sort of just stick just like that. We can let go now. And then I'm just going to put a little bit of fresh flux over this, and then we can reflow everything with the hot air. Or we can sort of just tap each side with the iron like this and make sure that those are some nice and solid joints. That thing is peaking, so we can throw a little bit more flux, and that looks perfect. Another way to do this is just throw down a nice pool of flux, and then just place the component generally in the orientation it needs to go. It doesn't have to be perfect. And we're going to lower our airspeed on the hot air station so we don't blow this thing around. Just going to go down to like 20 to 30% airspeed. And to compensate for the airspeed, I'm going to boost the temperature up to like a little over 400. And now we can just sort of come in with the low airspeed, and the surface tension will just pull the component onto place like that. And the amount of solder on the component ends up being more fitted for the component itself because it's just using the solder that's on the pads there. Whereas you can see with these other ones where I hit it with the iron, there's in some cases too much solder. Like this up here, that's too much solder on that side of the resistor. So actually we'll just like hit that up a little bit with the iron, and we can pull some of that off. There we go, that's looking a bit nicer. At least we could try to pull some of the excess off these as well. There we go, those are looking a little bit nicer. You can see what I mean, especially if I put it at an angle like this. You can see the component on the left is really just using the solder it needs, while the one on the right has quite a bit more solder than necessary on each side just because I hit it with the iron and the iron was tinned. Obviously either is going to work completely fine, but I just find this looks much more pretty than throwing solder on the components with your iron. So these capacitors are looking fine, and next we're just going to throw a nice healthy chunk of flux on these pads here. And I'm just going to tin my iron one side of the knife tip here, and we can kind of just drag over these. And if you go sort of parallel with the pads like this, you can see all this crap on here. I really need to replace my tip cleaner. It's especially obvious with the white solder mask. But as I was saying, if you just go sort of parallel with these pads, the parallel movements makes it so that they don't bridge. If you start going up and down like this, you start getting bridges like this. But if you go parallel to them, it's a lot easier to get nice puffy pillows that don't touch each other. So I'll just throw a little bit more flux on here because some of that flux came off. So let's just get this thing cleaned off. I never realized how dirty my flux gets while soldering. I mean, I'm always cleaning it off, but this white solder mask is a little eye-opening, honestly. So for these chips, this is the part number up here, and these are from Texas Instruments. So we're just gonna grab one of these for now and throw it down. And if we line this up, we've got the dot on the top left corner here, so we gotta line up the pin 1 on the IC with that corner. So I gotta turn this thing around. So this is exactly how we want this to go. For these larger chips, I really like to use these tweezers like this in the same way with the flat side towards the PCB. So I have a much better grip on this IC here than I did with the precision tweezers. And now we can just throw down fresh flux on these pads. And I'm gonna pop our IC in here, and we're gonna do the exact same method that we did for the capacitor. I'm just gonna use a lower airspeed. So 30% airspeed here, we're gonna go to 410, and I'm just gonna apply hot air. And for the bigger chips, they don't always pull themselves into place. You can see that kind of pulled itself into place in a weird way, so we kind of have to help it along. Just tap it, and that is looking pretty solid to me. We can let it sort of solidify, and then if we need to, we could grab it and sort of recenter it. So I could try doing that just to recenter it a little bit. And that IC is looking real nice. That thing's going nowhere. So I'll just get this area cleaned up, and I'm gonna move on to doing these other ones. And I'll just fast forward that or skip over that so you don't have to watch me do the same thing like 6 times. And for these, I will just go ahead and tin all of these things all at once, and then I'll go through and put all the components just to kind of make my life a little bit easier. And I do want to show too, you can do these without a hot air station. Just line it up like this, flip the whole thing around, and then just solder the other corner. And then you've got this thing nicely lined up, and you can go through, add some fresh flux on each side, iron on the legs, and go out parallel to the pads, and you won't bridge any of them with the flux, and these guys will all be nice and soldered to the board. Flip it around, same thing. So I just wanted to show that it is possible to pop these on without hot air, but hot air does make everything just a lot easier, to be honest. Cool, so we've got all of these in place now. There's a good chunk of flux on the board, so I'm gonna use one of these little foam cubes just to try to soak up a lot of that flux while it's still warm. And we can use this little brush here, get in between everything. Cool, so just got this all soldered and cleaned up, and it is looking beautiful. So all of the SMD components are taken care of. We just have to pop in this switch and the pin headers. And then I guess the Raspberry Pi is technically a SMD component as well, so we'll have to get that on here. All right, so here are the switches I'm using, and this is just going to slot in right here. This thing fits nice and snug. It's not really going anywhere, so we can just flip it over and get this thing soldered. Since these are through-hole components and this PCB is like pretty thick, I am going to just go ahead and use my Hakko iron with the larger tip on it, and this will just help heat everything sufficiently to get solder to go through the holes. So with through-hole stuff, you just want to leave your iron there for a sufficient amount of time to heat up both the board and the component, and to get solder to go through the hole completely to the other side of the board. And because they are going all the way through the board, you do need to use a bit more solder than you would think to really make sure it goes all the way through. And again, just be patient, leave your iron there for a bit. And I'll just melt some of the flux and we can get this thing nice and clean. It honestly probably doesn't make sense for me to be cleaning this along the way. I probably should just put everything on and clean it at the end. But I really can't help it with my workflow. I always like cleaning after working in an area. So you can see those joints are looking really nice because we use sufficient heat with a big tip. These end two anchoring points could probably use a little bit of a touch up. It's a bit harder to heat these two because they are a part of the shield here. So we can use some hot air to help us out to heat those up. So I might as well, I'll just go over these one more time, throw some flux on here. And I'm just gonna use like 380 just to really heat the board up. And then we can do the same thing on this side here. So those are looking a bit nicer now because there was enough heat on the actual metal itself for it to adhere well. Great, so we've got a nice little three-way switch here, working great. And we can move on to this sort of double pin header thing here. So let's grab the headers. These are the ones I'm using and they look like this. Nice little right angle thing going on there, and this is just going to go in the board just like this. So we've got all 24 little pin headers. For this, since I want it to lay flat and it's a little loose in the holes here, if I put it just like this and solder it, it's going to go on like at a weird angle like this. So I just want to hold this in, and I'm just going to solder in again like the two ends here while holding it with my hands, and that way it can be held in place and the way I want it to go on. So I'm just going to put some flux here. The point is not to make these nice yet, it's just to get this thing fixed into place while we get the rest of it soldered. So that's looking good. You can see this thing is nice and flat and it's not bent or anything like that. I think I'm going to go through all on this one side here and do all these and then flip the board just because it's easier to put my iron against the pins here. Cool, so now I'm just going to flip it, and same thing. I'm going to go over these end ones now. Have to add a bit more flux. Cool, so this thing is looking pretty nice. Can get this all cleaned up with the brush and some IPA. All right, we've got these beautiful looking joints here on this header. Even though we're not daisy chaining them, I'll just put one on here while we're at it because it's really not going to take that much more effort. So here is the female pin headers for that 3-pin thing at the top here. Again, just going to hold this in here. Get it nicely lined up. Turn my iron a bunch. Alright, and that's at least held into place now. And you can see the solder is coming through nicely to the other side as well. It's not just on that one side, but those joints are looking real clean. That's what you want. If you put too much solder, it's going to be a big ball. You want it to be these like nice little peaks with the ramps going up on either side. We could go ahead and do the other pin header over here. That is going to be these guys here. These are the male ones, and it's just sort of the opposite like that. And then same deal, just gonna hold this in place while we get this down. Just make sure that's nicely lined up. Yep, it is. And then we can get it properly soldered. Cool, so those joints look great. Again, we got solder coming through, except on this one. You see here, there's not really solder coming through on that. So I will just add a little extra solder to this guy here. And this is generally just a matter of either not having enough solder in there or not leaving the iron on long enough for it to travel through the board. Oh, and this is a great sort of example of there is enough solder in there, but there wasn't enough heat on this one on the right for it to actually stick to the pin. You can see the difference between the two pins on the left here and the pin on the right. Not enough heat was applied to this pin on the right for the solder on the other side here to stick to the pin. So ideally, we heat that up a little longer and it should solve our issue. So could add a tiny bit of solder too while we're at it. Just keep the iron on a little longer. And you can see it's looking a lot more like the middle one there where it's actually sticking to the pin now on each side. And the one on the left looks a bit different because it's a square hole. This thing is looking really nice. It's coming together. We just have to add the Raspberry Pi on here. And the one I'm going to be using for this one is the Pico 2. There's a few different models that he supports. You can check out the GitHub wiki. A link for that will be in the description. The reason I'm going with the Pico 2 for this one is because it supports something he calls blast mode, which will get this thing running at about 400 megahertz, which is going to kind of push this thing to its limits. So I bought some of these little mini heat sinks that I saw him putting on some of the ones he was building. And this should just give us a little bit of wiggle room with how much we push this thing. The reason I want to be able to measure at 400 megahertz is because I think the switch eMMC initializes at around 200 megahertz and then it jumps up to 400 megahertz. I'm not really interested in measuring 400 megahertz. If I was, we would need something a little bit more powerful than this. You generally want to be measuring at a significantly higher sample rate than what you're actually measuring. Measuring the 200 megahertz switch NAND is kind of pushing it a bit, but because we're using this for diagnostic purposes, and I'm not necessarily actually interested in decoding the actual data going to and from the NAND, I'm mostly just interested in making sure there is activity at all. I think technically if we were measuring a 400 megahertz data line, we would want something in the gigasamples. But again, we're not really looking for it to be perfect here. So let's pull the Pico 2 out. Here it is. And I don't think we need to solder these bottom three, so I'm just gonna do the edges here. But let's go into the microscope and put our little heatsink on here. Just get this thing cleaned off a little bit. I want it to make nice contact with the heatsink. And it's just like this thermally conductive adhesive there. And we can push down. There we go. That's perfect. You can see it's like a little bit bigger than the chip itself, which is great. It's going to provide some nice extra cooling for this thing. So I'm actually going to go ahead and just do the same thing here where I'm going to line this up and solder 2 corners. And then we can go through and solder the rest. Great. So this thing is nicely lined up now, and we can go through and solder all of these. So I'm just going to throw some flux across all these pads and on top as well. And I'll go through and tin these all first just to get solder sticking to all of them. Cool. And now we can actually tin the pads, and it will stick really nicely to these pads on the Raspberry Pi. You can see we're getting nice solid joints here between the actual board and the chip. Awesome. That side is looking really great. And now we can move on to the other side here. Great. So I got this side nice and soldered up as well. And now we just have to clean this thing up. Since there's so much flux on the board, I'm going to use one of these sponges just to kind of mop up a lot of it. You can see how much these help to get like lots of flux off the board when there's like big pools of it, just like that. Loving these things for this purpose. And now with the majority of the flux gone, we can come in with the brush and give it that last clean. All right, with that all cleaned up, all of those joints are looking really pretty. And this thing is complete. This thing looks really great with the green and white. I like it a lot. So here's the one I built, and then here's the one that we got assembled via PCB Way. I have to say PCB Way did do a little bit of a better job centering those voltage translators there, but I think I did pretty good. Really happy with how this came out, and we can go ahead and get some firmware put on here. So to get firmware on this thing, we just have to head over to the GitHub, and you can just go over to the releases section of the GitHub. And this most recent version doesn't have any of the firmware in it, so he just mentions to go to release 6. So we're gonna go down here, go to assets. We've got all of these different firmwares for the various Pico boards. So in this case, I'm just gonna grab the one for Pico 2, and you can see it's downloaded that right there. And here's the firmware file inside of the zip, so we're just gonna unzip that into a separate folder here. All right, so I've got a micro USB cable here plugged in my computer. And since this is a brand new Raspberry Pi, we should just be able to plug this in and see it pop up on the computer. There it is. Don't judge my full hard drives. I have like so much 4K footage I have to deal with. So here it is. It showed up as RP2350. If you don't see it show up, you can just hold the boot button while plugging it in, and that should do it. And then we can just drag this firmware over here. And when I let go of this, we should see a light on here, I believe. There it is. And this thing is on now. So next, we're just gonna come over here and grab the all-in-one for Windows x64. And this is what you get in the zip. I'm just gonna extract all of this into a folder on my desktop. And now we can just click on the logic analyzer. And here we go, we've got the logic analyzer software opening. I love the little splash screen. So here we have the logic analyzer. And I'm just gonna try to click auto detect and see if it can't find it. And I'll click open device. And there we go, it detected that we've got the Pico 2 logic analyzer hooked up, and we can press the info button here. And this is just giving us maximums and minimums for our specific analyzer. So I think this should be 400 megahertz for this particular chip. I may have to put a different firmware on here though for this to be 400. There was one called like turbo, so let's try that after this. And we've got a buffer size, and for up to 8 channels, it looks like these are our maximums for pre and post samples. And then we've got some smaller maximums for the 16 and 24 channel. But this is really where we're mostly operating here with this top half of this information. So what we're gonna do here is I have a switch motherboard, and excuse this whole mess here, but really all this is just wires. So we've got 4 wires that we're working with. The red and white here is going to translate to the red and black. And this is going to be for our reference voltage. We're gonna be reading a clock signal, which I believe operates at about 1.8 volts on the eMMC here. We're gonna set the reference voltage on my power supply to like 1.5 volts. So in order to set the reference voltage, I'm just gonna make sure this switch is set to the external option. And then we're gonna take our red and black, and you can see we have VREF for this second pin here. So I'm gonna put the red right there. And then the black is the ground right next to it, just like that. And again, that translates to our red and white wire here. And I'm just going to use my bench power supply here to supply a reference voltage. So I'll just use these alligator clips here, and I'm going to set my bench power supply to 1.5 volts. Just set it to like 500 milliamps, is probably fine. Just turn it on. So the voltage reference with a logic analyzer like this is the voltage at which the analyzer is going to indicate whether or not the data coming through is a 1 or a 0. So if the data coming through on pin 1 of this little pin header here, for example, exceeds the voltage reference set up here, it's going to count that as a 1, and then anything under that is going to count as a 0. And then we also need to connect ground up to the device itself that we're measuring to. So we're going to do the yellow wire, and that's going to be the bottom ground here. So this bottom one, so you can see those two are ground. Top one I'm using for the reference voltage. Bottom one I'm using for the actual board. And then we're just going to use one channel for now to test this thing. So I'm just going to go with this first channel here, which is right up here. And we're going to use the green wire for that. So all we have to connect here on the actual device that we're measuring is ground, which is going to be this yellow wire. So I'll just go ahead and solder this to like the USB-C port here for ground. And this green wire here is going to act as our probe, and we're going to measure various data points. So for example, on the switch, I know that there is a clock signal right about here. So my thought process here is to try to measure the clock signal with this little probe while turning the console on with the battery plugged in. So I'll go ahead and plug the switch battery in. So console's not booted yet. We're going to have to boot it using tweezers here. And if we go back over to the logic analyzer software here and click capture, you can see right now we're running at 100 megahertz. But I'm going to check blast mode here to go to the highest frequency possible. And then we're also going to set this to the maximum as well. So this is going to be our maximum amount of samples it's going to take. We can name this if we want. We can just name this clock, I guess, because that's what we're going to be measuring. And I think for blast mode, we can only do a edge trigger. That works totally fine because as soon as the clock signal gets detected, it's going to start recording, and it's going to record 390,000 samples. So I'm just going to go ahead and say accept. And now it's attempting to capture. It's not capturing anything yet because obviously there's no voltage detected or high detected on this probe. So all I'm going to do is just hold this on the clock point here while booting the console. Oh, and we did get a actual recording here. And let's see if we got, hey, look at that. That's so cool. I think we can increase the samples. Yeah, this is really cool. So this is the clock signal for the NAND on the switch. And you can see here all of the samples it took. So you can see the clock is running on the eMMC. So technically right now we're measuring at the exact same rate as the clock signal. So this is probably not 100% accurate what we're seeing here. But for repair purposes, I don't really care. Like, I just want to see if the clock is running. And we can see here it's very obviously running. I want to go back over to the firmware here, and let's try this Pico 2 Turbo firmware. All right, I've got it extracted here. And in order to rewrite the firmware on this, we just have to hold the boot button while plugging this thing in, and it should show up. And here it is. It's showing up again. And I'm just going to drag the turbo firmware in here. So that seemed to work. We've got the green light again. And now let's try opening this again. Oh, perfect. Yeah, so we can see this changed to 400 megahertz for blast mode. And then normal operating, it's going to do 200 megahertz. So I think I was correct in assuming that the turbo firmware is for the higher frequencies. So it's cool because we managed to verify that this thing is working. We can detect the clock signal on the switch. And I'm really excited, especially for a PS5 repair, to start being able to read the data going between the South Bridge and the NOR. We should be able to hook up a few different channels and see all the communication happening. We should be able to compare working consoles and the way those communicate versus how, you know, a console that's giving us trouble, maybe there's an issue with the South Bridge chip, or maybe there's an issue with the NOR. And we'll actually be able to see that at the same time, which one is talking to which with the different channels. So I had a lot of fun making this device. Thanks again to PCB Way for sponsoring the video. I appreciate you guys for watching, and I will see you in the next video. Peace.